Okay, thank you for that introduction, Hans. Moving on now to a talk that covers work package 2 of the METMAGS project. I'm Michael Hall from NPL, and I'm going to be talking about the facilities that we have here at NPL for the calibration of magnetic sensors, focusing mainly on the low magnetic field range, and I'll introduce the facilities we have in our low magnetic field laboratory, which is on the other side of the site here at NPL. And the title of the talk is, well, we need reliable magnetic sensors. How can we be sure that the characterization of those, the calibration of those sensors meets the required end use, and that the uncertainties that we have for those calibrations are also suitable for use. So here's a slide to summarize what I'm going to cover today. We're going to look at the existing NPL low magnetic field facility. We need to improve that facility, and I'm going to explain why and the approach that we're taking to do that. And for that work we're collaborating with the Mendeleev Institute in St. Petersburg, Professor Vladimir Shiffrin. I'll move on then to noise measurements at 0.1 millihertz and how we have performed these measurements for an ESA project. I'll look at NPL low magnetic field standards, which includes gradient coils. That's a new field standard that we've recently added. I'll explain why that was needed and how we have calibrated, and how that coil system is then used to calibrate the customer ESA, in this case their gradiometer. Look at the tensor components, and then I'll move on to AC measurements, what capabilities we have, how we calibrate the coils that are used to perform the calibration, also in the low magnetic field lab, of AC sensors. And I'll give a couple of brief examples of projects which have been performed using the facilities that I've covered in the low magnetic field lab. Here's a picture of the facility that's over in Bushy House. What we're looking at there is a 3 meter diameter 3-axis Helmholtz coil system, and we can see in the picture some of the formers that are used to apply onto these formers. The windings are applied that are used to remove the ambient magnetic field that's present in this laboratory. We can see this is the surface here of one pair of formers, and we can see here 2 other coils which form the Helmholtz coil on another axis, as well as the Helmholtz coil on this axis. The coil that's in the centre is a 1 meter diameter Helmholtz coil, and it's being used to calibrate the 3-axis fluxgate magnetometer along one of the axes, and the axes are done, each of the axes are done individually, and there the guy is setting that up in the centre of the system, and it's in this region where the larger coil system has cancelled the ambient magnetic field down to less than 1 nanotesla. I'll talk about the noise floor on that, and limitations, and how we are planning to improve and reduce that noise floor in the next few slides. So what have we currently got? Well, the system that I've just shown in the previous slide, the picture of that system, that's an open feedback 3-axis 3 meter diameter Helmholtz coil system. And what I mean by open feedback is the magnetometer, little black box that was being positioned in the centre of that facility, that is used along with a second identical 3-axis fluxgate magnetometer, which is remote 70 meters away, to reduce the ambient field down to less than a nanotesla. And then we have to apply fields so that it's removed. That fluxgate in the lab is removed. So during that time that we're applying our fields by measuring the current through the calibrated Helmholtz coil, 1 meter diameter Helmholtz coil, the system, the ambient, can drift slightly. So there's always a possibility of having this drift occurring. which will appear as a variation in the background and ultimately could affect the uncertainty of our measurement. So we want to close that feedback, and in doing so that'll give us more stable field readings and lower the noise that we have on our magnetic field levels that we generate. And these points here, the last bullet point, they're just summarising that we can have this drift during extended measurements, and extended there meaning maybe 5 to 10 minutes. At the end of those measurements we would then put our 3-axis flux gate back in to the system and measure what the field was, and if it had drifted too much it would be necessary to repeat. So that is a weakness which we can overcome. Here's a little schematic that shows what I've just described, and what we have is the remote flux gate magnetometer, which is 70 meters away in the garden, and we have the 3-axis flux gate we saw in the picture positioned in the 3-axis at the center of the 3-axis Helmholtz coil system. And the remote flux gate, the outputs from each of the axes, then feed into 3 separate power supplies, servo controlled inputs, which then generate the currents that go into each of the coils of the 3-axis Helmholtz coil system. And what we can do is just trim the output of these amplifiers to get that to be 0 before we start our measurement. And here we can monitor what the output of that is, and use the trimming of the gain and the offsets to get that to be 0 before we begin. What performance is achieved? Well, we see here in this slide the ambient variation is the black line. So seeing changes there that can be of the order of 100 nanotesla or so over a period of a couple of minutes. And here we have just over 1,000 seconds on the time axis. So if we were trying to calibrate a flux gate magnetometer in there which has got a noise floor, say resolution of sub nanotesla, then we would be having a massive contribution to that calibration from the background. Even by doing field reversals, that takes a finite amount of time, and this field can be swinging around by tens of nanotesla during that time. So our repeatability would be poor because the background was poor. So if we operate the system and use the signals from the 3-axis flux gate in the garden, we end up with the red line when the cancellation has been applied. And as you can see, a considerable improvement. I'll talk about the noise that we achieve on that cancelled environment in the next couple of slides. But it is a significant improvement, and the origin of these variations in the ambient magnetic field are due to the electrified train system that we have here in the Teddington region, in this part of London. And that system works by a third rail, which provides the power. That rail is insulated from the ground, but the return circuit is on one of the running rails, and because they're load bearing, they can't be insulated, and we get leakage currents into the ground. Those leakage currents, if you do your right hand grip roll, then generate magnetic field. The field that we see here in this graph is the vertical field, and that corresponds to the field direction for these leakage currents. So we have to set the system up to be able to live and remove those changes. So what happens if we say we use that low magnetic field cancelled environment, where we reduce the ambient down to less than 1 nanotesla to calibrate, to generate magnetic fields? What's the uncertainty that we have? Well, because we've got such a quiet environment and we have no variation, very, very small variation in the ambient magnetic field, the repeatability is excellent, and the contributions to the budget on measuring a magnetic field are actually very small. And here we see a budget with the expanded uncertainty, so that's a 95% k equals 2 uncertainty, rounded up to 0.003%. That's on the measurement of the magnetic field. When we use a Helmholtz coil to generate, we of course measure, so this budget applies, and we have some additional terms for measuring the current that goes through the winding and on the actual determination of the coil constant. Very low uncertainties, which provide a very good basis for calibrating flux gate magnetometers, as well as other very sensitive magnetic sensors, such as those based on GMR, GMI, and other quite new phenomena based on magnetic thin films. So what we're doing at the moment is lowering that noise floor to with a target of 1 picotesla per root hertz at 1 hertz, and compare that to the existing noise floor. So that red line in the graph I showed earlier, that's 20 picotesla per root hertz. So to get it down to 1 picotesla per root hertz, we've got a considerable improvement that's required, and we have an inherent noise floor of the flux gate magnetometer that's used, and that is measured and is known to be 7 picotesla per root hertz. So we have to move to a magnetometer technology that has a noise floor of 1 picotesla per root hertz or better. So we looked into this, and we therefore selected atomic magnetometers, and we're using a cesium magnetometer, which has got a stated noise floor of 0.5 picotesla per root hertz at 1 hertz. And what we are going to do with that is to close the feedback loop that I discussed earlier. And we're going to use what's known as a single volume field stabilisation approach. I've got a slide in a moment which will show what that means. But it's a hybrid approach in which the 3-axis flux gate magnetometer that's in the pit in the garden will still be used to cancel field in the vertical direction and also in the east-west direction. And in the north-south direction, we're going to stabilise the field using the cesium magnetometer. So it's single volume in the sense that the cesium magnetometer will be placed inside that cancelled field environment, but we will use the 3-axis flux gate. So a kind of hybrid approach. It's not fully what's known as second volume, because in that case, a 4-second volume approach, you have a identical scaled down coil system remote that is used to generate the currents in your coil system, and that scaled down coil system has an identical coil constant, and it's quite hard to establish. But we are already in a position where we have a good cancelled environment, so we don't have to go to those lengths, thankfully. So it is not easy. So the single volume field stabilisation, we have the field that can drift during measurements, and we will stabilise those with a cesium magnetometer. The one we're using is a Syntrex CSL magnetometer with a range of 10 to 100 microtesla. We will have the CSL magnetometer in the cancellation system, so when we want to generate a field, we will use additional windings that need to be placed on the north-south axis formers, coil formers, and there's additional winding. There will be 2 of them. One will be used to generate that field target that we require, and then there will be a variation winding that will be used to stabilise it, and the current in that variation winding will be controlled by the output of the cesium magnetometer. Hence we achieve the stabilisation and stabilisation control of the field through the current, and that's from the output of the magnetometer through a phase detector which drives the current. And because there could well be a variation in the magnetic field within the coil system, because it's not perfectly uniform, we were using a static coil to compensate for that. And it's worth mentioning at this point that is one of the major advantages actually of this approach of having your stabilizing magnetometer in the coil system, is that gradients that occur between your reference magnetometer and your environment that you wish to have cancelled field in are a limiting factor on the performance that you achieve. For example, with our existing setup and the fact we have 70 meters between our reference magnetometer and our lab, if there is a difference in the magnetic field that exists in those 2 locations, and here we're assuming that our building doesn't contribute any field gradient, thankfully. It's a very old building built in 1660 something, so it's got no steel in its construction. It has no magnetic signature, very, very small magnetic signature, unchanging, which is also very important. Those two fields, if those two positions are different, they will be different. Hence, our performance cannot be as good as, say, the noise floor of the cesium magnetometer. We've got to reduce that distance, hence the single volume approach. This very busy slide here shows a kind of summary of different approaches that can be used, single volume and two volume. And really all I wanted to say about this particular slide is that we have a cesium magnetometer here inside of our 3-axis Helmholtz coil system, so that we don't suffer from the gradients that I've just described. Any gradient will be considerably smaller, and using a static coil we can compensate for that, plus any non-homogeneity of the field. Noise measurements. Well, to do very, very low frequency noise measurements over long periods of time, you need to have a very, very stable zero environment, and a cesium magnetometer, of course, will give us a stable field over a very long period of time at a field above 10 microtesla. At zero, what we can do and what we've done is to use our cancelled environment, which is getting down to less than 1 nanotesla, and a 3-layer shielded can that is positioned inside that environment, to attenuate the residual remaining field even further. And that takes out, removes to a sufficient level any of those drifts that are going on in the system. They are attenuated right down into well below the noise floor of the best magnetometers. We also have to be aware here of thermal drifts, so we have to thermally stabilise this 3-layer can, and to do that we've put it into a thermal chamber and measured the temperature inside that chamber over a period of over a day, and it's very, very good. In fact, you can see there on the third bullet point it's 0.05 degrees centigrade over a 24-hour period, so thermally it's been nicely stabilised. And we need to do that because if the temperature is drifting, then we have a fluxgate magnetometer in there to measure what the field is. That will also drift because the offsets have a temperature coefficient, and that will therefore appear as some noise. So what we have is a further attenuated field, stable temperature-wise over a long period. We can measure that field, that's residual field in there, over 24 hours, and in that calculate the environmental noise at 0.1 millihertz. And 0.1 millihertz is important for space applications. ESO have a need, and Doug Griffin will be talking about that in the next presentation. And also in any long-term observation of magnetic field levels for geomagnetic activities, geomagnetic studies, you need to have good noise performance at very low frequency. So what we have here is 475 picotesla at 0.1 millihertz, 475 plus or minus 220 picotesla per root hertz. That plus or minus 220 comes from the fact that we've made many, many observations. We are looking here at a random noise, so we have quite a wide distribution on our values. The target there was less than 1 nanotesla per root hertz, so we're comfortably inside of that, and there is evidence to show, we believe from that evidence, that the noise at 0.1 millihertz inside of that shielded environment is limited by the fluxgate magnetometer that we're using, which is a Bartington 3-axis fluxgate. And Olivier from Bartington will be giving the talk after Doug, linking through into fluxgates and their use for magnetic field, very low magnetic field measurements. So if we could get a sensor that had lower noise floor than the Bartington 3-axis fluxgate in that environment, we'd get a better feel for what the ultimate noise performance is. And PTB and Thomas Schurig, also of Work Package 2 at the METMAX project, they have their squid systems, which we're discussing on looking into using those to establish what that noise floor of the environment actually is. And a comment now on the time series analysis, which is using a PSD approach, and that LTPDA toolbox is something that ESA requires everyone to use so that you have consistency in the analysis to get the noise spectrum. We also measure offsets in this CAN. And here's a plot of what the measured noise performance looks like. And at 0.1 millihertz, we can see there that we're getting this 475 picotesla per root hertz noise performance in the CAN. Better than that 1 nanotesla per root hertz target. Okay, I want to move on now onto a gradient tensor and a gradient fill standard that we now have at MPL. Shown in this slide is the gradient tensor with its 9 components. We have the 3 diagonal components, and then we have the off-diagonal terms, 6 of those. Thankfully, if you wanted to calibrate a gradiometer, doing all of these terms would be a lot of work to do all 9. But thankfully, because of the Maxwell equations, we have the ability to reduce that number. We have these terms which are equal because the curl of B is 0, and also we have the trace of this matrix has to be 0 as well, so that we only have to determine 2 of these, and therefore we can then calculate the third because the sum has to be 0. So as a consequence of that, there are only 5 independent gradient components that we need to determine. This is the MPL gradient coil that we have now in place, so designed, analysed in detail so we get the field profiles from that, a design and a build here at MPL over the last couple of years. Something of interest to note here is the winding that we have on each of these formers. The conductor there is capable of carrying up to 20 amps. The target field gradient here was 50 microtesla per meter, but we need much more current to generate higher fields so that we can actually calibrate that Helmholtz, so that gradient coil system, using a very small sensor so that we can get the spatial resolution using a Hall probe. So we need to pass 20 amps through. In practice, when it's being used, we're probably only putting a couple of 100 milliamps through to generate the gradients that we need. And the gradiometer would sit here in the center. So we have 50 microtesla per meter as the required. We used the analysis tools of Opera 3D to model this coil system and optimize the position of the coils and also their width. The width that was suitable for the winding that we needed, so that we had the most uniform field region. And the gradient is uniform to 0.05% over a length of about 50 millimeters at the center of the coils. Also, it's worth noting that you have a uniform dBy by dy and dBz by dz achieved at the same time. But if we go back to that gradient tensor, because we're generating a uniform gradient, by definition these off-diagonal terms are 0. So in order to calibrate these off-diagonal terms, we have to apply a little clever trick. And what we have done is, when operated as a gradient coil, the currents in these 2 windings are in opposite directions. So what we do is to apply the current in these 2 coils in the same direction. So then we go to the world's worst Helmholtz coil system. And in using that approach, we can generate off-diagonal terms. And I'll show you some profiles that we get, and it gives us a means of being able to calibrate off-diagonal terms for the gradiometer being calibrated. And that's summarised there in that last point. A good gradient coil does not produce off-diagonal terms just because the matrix tensor shows that you can. This is what the profile looks like on the gradient coil that we have, and you can see that the variation over plus or minus 10 millimeters in the center of there is less of the order less than 0.01%. So that's very, very good. This is a mount that we have for putting a gradiometer from ESA inside of that 3-axis Helmholtz coil system. Inside of that gradient coil system, gradient field standard. And it's designed so that we can accurately turn the gradiometer head through 90 degrees. And the angle between these faces have been measured, and also we've got some crosshairs there so that we can align the physical housing of the gradiometer with the field direction within the coil systems. So that goes inside the gradient coil, inside the 3-axis Helmholtz coil system, and actually it can also go inside of a Helmholtz coil system to apply biasing fields, which are also important. So let's have a look here if we have this set up as a Helmholtz coil to look at these off-diagonal components. And you can see here now that we don't have, as you would have for a gradient coil, a nice linear field with distance. We have this variation, considerable variation of field with distance. And if we just focus here on the region around x equals 0 and make a plot against these different y positions of the field that we get, the result is shown in this next slide, where we can then see that it's not in any way linear, but it's varying nice and smoothly with y position. So the principle of doing off-diagonal calibrations is to position your gradiometer aligned and positioned, make a measurement, and then shift it by a known distance and repeat that. And effectively what you do is trace along this curve, and this is then used to determine, to infer what the baseline is for the axis of interest. And then once you have that baseline, then you have means of establishing the calibration for that axis. This here shows that when you do have a non-uniform field and we're running it in this Helmholtz coil mode, you will have sensors in slightly different positions. Well, if you then look at how the field varies at those different positions, they're on top of each other to a level where any uncertainty contribution due to that is absolutely tiny and is in no way significant for the overall uncertainty. You can see that by how well these two curves lie on top of each other. Right, I want to move on now to AC field generation, still done in a low magnetic field lab because we have a nice clean AC magnetic field environment. The main circuits are non-inductively set up, so that AC fields at 50 Hz are very small and sources of other AC fields are pretty much non-existent in that location. So we have two Helmholtz coil systems. We have one which is capable of 2.2 milli-Tesla at 50 Hz, and we have a coil system that is capable of 70 microtesla, only 70 microtesla at 120 kHz, but that is high enough. We're talking here of the calibration of instruments used for exposure studies. 70 microtesla is fine. And the apparent change in the coil constant with frequency for that 120, that high frequency Helmholtz coil, is about 1%, and we have an uncertainty we can correct for that, and we have an uncertainty overall on the AC calibration of about 0.5%. So, and here we see a picture of that 1 meter diameter AC. This is the lower frequency, 50 Hz, 2.2 milli-Tesla Helmholtz coil, and it's being used there to calibrate a 3-axis meter used for checking exposure levels. That's the item we can see here. So how do we calibrate the high frequency Helmholtz coil? Well, we're in the low magnetic field lab, so we do a DC calibration of the field to current ratio, and that is done inside the cancelled environment, so we have a nice and very low uncertainty on that. We then use a large aerial single turn surge coil, and we don't have to worry about the fact that the field through that is not uniform for the whole area, because we're here interested in only the frequency response. The fact that it's single turn is the important thing. It's big enough to give big enough output to measure with low uncertainty, and because it's single turn, there's no intra-winding capacitance that's going to give us any frequency dependence on the area, the effective area of that coil. And we use shunts which have known AC/DC difference, calibrated at MPL to measure the current that's flowing through the coil, and we therefore determine the coil constant against frequency through a combination of this DC value and the AC frequency response that we measure with the single coil. And this is the behaviour that we get. So as we go up in frequency, the coil constant increases with frequency, and that is because we are measuring the current outside of the coil system, and the current which is actually in the windings is larger because of the distributed capacitances across the windings. So therefore the coil constant apparently increases as we go up in frequency. Right, a couple of quick examples on how we've used the low magnetic field for facility for customers who otherwise would have, they just could not do the measurements themselves. This here is a picture of a portable 3-axis flux gate magnetometer system. Here we see the head, and here we see the electronics and the battery down here to power it with the DVM for readout. That was taken to London City Airport nearby. It was necessary to measure at a number of points on a defined grid what the magnetic field was, and this was needed because of an incident, this is in public domain, where a plane that was landing turned into the flight path of a plane that was taking off. So the plane that was taking off turned into the flight path of the plane that was landing, and with therefore generating a near miss. And they needed to understand where that was coming from, so we did the survey. We found that it was down to some of the steel casings that were used on the piles, and from that information London City Airport were able to go to the authorities and get permission to do an extension of their facilities and their apron at the airport, because they could show that they understood what the cause of the problem was, and they could put mitigation in place to prevent it happening again. You need to do very sensitive magnetic field measurements using a flux gate which is calibrated in our low magnetic field facility. And a little bit here on an AC study that we did for what is probably the world's worst mobile phone handset. This is a instrument, effectively, that's been knocked up for a double-blind study, so it's not a handset you'd buy in the shops, not that you'd sell many of them anyway. And what we were interested in here was not the RF frequency, but the fact that because of the time series modulation that goes on during RF communication, you have a varying duty cycle on the battery, and that varying duty cycle on the battery generates a varying current within the handset, which therefore generates a varying magnetic field. And we needed to know that the magnetic field produced was below the guidelines of the Health Protection Agency. And that's the type of time series that is generated by such a handset when it's running the GSM time sequence. And the outcome of that work was that these are the HPA guidelines for the exposure levels, and these were the measured values, and everything is fine. And without being able to calibrate the sensor that was used in the low magnetic field laboratory, measuring this would have been very, very difficult. In fact, because of the bandwidth we wanted, you could not use a commercial instrument. We had to build one and characterize it in that facility. So, to conclude, we have the low magnetic field facility that is in Bushy House, which has the noise floor being stabilised, being improved to 1 picotesla per root hertz at 1 hertz. We've got magnetic field standards. I haven't talked about UCAS, but they're all accredited by the United Kingdom Accreditation Service, and this is required by a lot of companies for their own quality systems. And we use these field standards for our measurement services and also for R&D projects. And the next talk by Doug will talk about the ESA project that has been running, and we're calibrating the gradiometer at MPL now. And also we do instrument calibrations for instrument manufacturers like Bartington, and that'll be the talk after Doug. We have a very low uncertainty, 0.003%, and what we are always doing is looking to continually update and improve those facilities. So we're improving the noise floor and closing the feedback to get the stability, but we need to add some temperature capability. into these calibration services. And we're going to be talking about that later on today. And as part of the METMAX project, MPL will be establishing a temperature range of at least minus 40 degrees to 100 degrees. The final range will be decided as part of this panel discussion, and we'll communicate it to everyone here when that's been done. So thank you for your attention, and yes, enjoy the rest of the day. Thank you.